So we've been talking about things like Taylor series. So if we have a function like e to the x, we can write it as this ever-increasing list of approximating polynomials, 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and on and on and on and on. Now, in the process of making these Taylor polynomials, it turns out that we've been actually paying attention to certain lists of numbers. For example, we've been focusing on the lists of numbers that go in front of the powers of x, the 1 over 1 factorial, the 1 over 2 factorial, the 1 over 3 factorial, the 1 over 4 factorial, right? It was finding a pattern in these numbers that was extremely important to us in coming up with formulas for the Taylor series of certain functions. The flip side, or the other one that we've been focusing on, is when we actually go and plug in a specific number, such as, say, approximating e to the negative 1, where we would go and plug negative 1 and get a list of approximations. So there's the approximation 1 plus 1 over 1 factorial times negative 1. And we'd get the better approximation of 1 over 1 factorial negative 1 plus 1 over 2 factorial times negative 1 squared. And we'd get an even better approximation of 1 plus 1 over 1 factorial negative 1 plus 1 over 2 factorial times negative 1 squared plus 1 over 3 factorial times negative 1 cubed. And every single time we add a new term, we get a slightly better approximation than the version that we had before, on the assumption that we're staying inside the radius of convergence. But this collection right here that I'm putting in these big giant braces, dot, 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 is just another list of numbers. And this time, successive lists of approximations of the value of e to the negative 1. In both cases, we're talking about infinite ordered lists of numbers, which in math is called a sequence. So, this first example right here is sometimes called the Taylor coefficient sequence, because they tell us the numbers that go in front of the terms in the Taylor polynomials. On the other hand, we have here the Taylor approximation sequence, the list of numbers that give us better and better and better approximations of a Taylor or of a function by evaluating it at its Taylor polynomials. And so what we want to do in this topic is to talk about the mathematics of sequences and what are some of the important ideas that help me to figure out what a sequence is, what the terms of a sequence are, and what kinds of things we're going to do with it in order to help us understand the Taylor and power series ideas better. Now, a sequence is an infinite ordered list of numbers. So something as simple as 1, 2, 3, 4, 5 would be an example of a sequence. More generally, if you just had any list of numbers, we typically denote the first one as A0, followed by A1, A2, A3, and on down the line. So this first entry is sometimes called the zeroth term, or the initial term, and then we have a first term, and a second term, and a third term. This is one of the few times where we sort of count like computer scientists in a math class by starting our counts with 0. So a sequence is simply an infinite ordered list of numbers. Traditionally in mathematics, we list the terms of a sequence and then we put a set of curly braces around them to sort of indicate that they're all part of this one collection, this one object that we're going to call a sequence. If we use the letter A to denote the individual entries, then we sometimes write a sequence compactly by saying curly brace A and curly brace n going from 0 to infinity, which is supposed to be read the sequence an going from 0 to infinity. And sometimes if we're just really, really lazy, we drop off these two things and just write curly brace an curly brace. So, for example, if I had the list of odd numbers 1, 3, 5, 7, 9, 11, going on and on and on, I could put these things in braces to indicate that it's a sequence, and then I could give this sequence a name. Let's call it little o of n for the odd numbers. And so what this is telling me is it's telling me I have a sequence whose terms we'll call o. So if I want to talk about the second term in my odd sequence, what would be my second term? Well, this first one would be odd 0. This will be O1. And this one will be O2. So O sub 2 would be 5. That's my quote-unquote second term in the sequence. Remember, we start counting at 0. And if I wanted to talk about O of 4, well, the count is 0, 1, 2, 3, 4. And so O of 4 would be 9. And that's just how the notation works. So the basic idea is if you give me any number, 3, then there is a term in the sequence who corresponds to it. In this case, O of 3 would be 5. So that idea of you give me a number, and then there is a term in the sequence who matches it, would suggest that these guys are functions, a special kind of function. These are functions whose domain consists only of the numbers 0, 1, 2, 3, 4. So if I were to plot a set of axes, 0, oops, I'll put that in the right spot, 0, 1, 2, 3, 4. Normally when we have a function, we have lots and lots and lots and lots and lots of little dots, and we connect all these little dots together in a smooth curve. But for a sequence, you only have dots at the integer values. So at input value of 0, we would plot this point right here at, say, height A0, and this would be the ordered pair 0, A0. And then for an input value of 1, we might have some other dot. So this might be the point at 1, comma, A1. And so we could do the exact same thing. So at each point, we might have a dot at a different spot. But unlike the functions that we're so used to in our Calc 1 class, there is nothing that connects these guys in between. There isn't an A1 half, or over here an A pi wedged in. There's a 0th term, a first term, a second term, but there's nothing in between. So in some sense, sequences are the theory of really disjointed, disconnected, discontinuous kinds of functions. So what do we want to be able to do with this idea of an infinite ordered list of numbers? Well, it turns out that there's two useful skills that will serve us well in calculus and as engineers, as scientists. Skill number 1 is to be able to find a formula for the terms of a sequence. The second skill is to find the limit of a sequence. And so it's most helpful to explain what these two concepts are by looking at examples. And so let's take a look at several examples. So here's a list of 6 different sequences, and for each one of these sequences, let's try to do the same thing. Let's see if we can find a formula for the sequence. So what this means is can we find some special formula who would say, give me the nth term of a sequence. So let's start off with this first example, example A, and let's, for the time being, call this the sequence AN. So what does that mean? Well, it means that A0 is equal to 1, A1 is equal to 4, A2 is equal to 7, and A3 is equal to 10, and so on. And so what we'd like to do is we'd like to come up with a formula, AN, which would somehow sort of magically generate all of these terms. But what would this formula be? Well, the key to finding formulas for sequences is, in some sense, the same trick that we did in finding Taylor polynomials. You hunt for patterns. Now in this one of the ways to start off is to sort of figure out what you think the next several terms might be. So if we look at the terms we've got right now, 1, 4, 7, 10, and then there was a 13 and a 16, what would be the next couple of terms? Well, if you stare at this for a while, it seems like we're adding 3 each time. 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 3 is 10, 10 plus 3 is 13, 13 plus 3 is 16. So it seems as though if I keep adding 3's, that might be the next several terms. 19, 19 plus 3 is 22, 22 plus 3 is 25, and so on down the line. So does that help me out? Well, actually, it does a pretty good job, because let's see if what I've got. I know the first term was 1. The second term, writing it out without simplifying it, trying to think of the same thing I do when I'm working with a Taylor series, I could write this as 1 plus 3. The next term was the previous term plus 3. The next term, A3, was the previous term plus 3. And then the next term down was the previous term, 1 plus 3 plus 3 plus 3 plus 3 plus 3. And on down the line. So let me take a look at what I've got, hiding some of the details in the middle. I've got A0 is 1, A1 is 1 plus 3, A2 is 1 plus 3 plus 3, A3 is 1 plus 3 plus 3 plus 3, and A4 is 1 plus 3 plus 3 plus 3 plus 3. It seems as though each time I'm adding a certain number of 3's, and the number of 3's I'm adding is exactly what the subscript is. So based off of this, it would seem as though A sub n is going to be 1, and then we're going to add 3 n times. And so we've managed to dig up a formula for A sub n. And we could check that it works. If I had, say, A sub 4, this would say that A sub 4 is 1 plus 3 times 4, which would be 13. And if I check, A0, A1, A2, A3, A4. And so this works. This first example, the sequence AN, is an example of something called an arithmetic sequence. The idea of an arithmetic sequence is one in which each new term, A sub new, is equal to the previous term, and you add the exact same constant k each time. In this example, that constant was 3. Generically speaking, the constant might be something else. If you happen to have an arithmetic sequence, then the formula for any arithmetic sequence is a lot like the one we've just found out. It's A sub n is equal to A0, whatever you started off with, and then you keep adding this k n times. And so this is the general formula for an arithmetic sequence. And we'll actually use this from time to time. So cool, we've got the first one taken care of. Now let's focus on sequence B. So let's first off name this as the sequence B sub n so that we can refer to the individual pieces. The terms we've got, B0 is 2, B1 is 6, B2 is 18, B3 is 54, and B4 is 162. What patterns can we deduce from this? Well, I'm not adding the same thing each time. From here to here I added 4, but from here to here I added 12, and from here to here I added, well, neither 4 nor 12. So I'm not adding the same thing each time. But if you stare at it long enough, you might figure out that I'm multiplying by 3 each time. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54, and 54 times 3 is 162. So I'm adding a 3 each time, or sorry, multiplying by a 3 each time. So can we come up with a formula for this like we did the last one? Well, let me get myself some scratch room here. We started off with 2. The next term was 2 times 3, and then each new term was the previous term multiplied by another 3. So for example, that 54 was 2 times 3 times 3 times 3, and the 162 was the 2 times 3 times 3 times 3 times another 3. So each time I'm starting off with the 2, but I'm multiplying by a certain number of 3's, and the number of 3's I'm multiplying seems to be what the subscript is. And so generically speaking, it looks like our nth term is going to be 2, and then we're going to multiply it by 3 raised to the nth power. And so we have a formula for the second one. In fact, this second example, Bn, is an example of something called a geometric sequence. A geometric sequence is one in which each new term, A sub new, is found by taking the previous term and multiplying it by the exact same constant. So you multiply by 3 each time, or you multiply by 7 each time. And just like the example down below, to get the formula for the nth term of a geometric sequence, well, you start off with A0, and then you keep multiplying by k raised to bigger and bigger powers. So every geometric sequence has a fairly nice formula. And arithmetic and geometric sequences, they pop up quite a bit. So we've got the second one taken care of. Let's move on down to the next sequence. Oops, it just occurred to me that I actually haven't written the formulas down here, so let me go back and fix that. The formula for this one was 1 plus 3n, and the formula for this one was 2 times 3 to the nth power. So let's move down to this next sequence, a sequence who we could call Cn. So the numbers are 1, 1, 2, 6, 24, 120, 720. If I sort of keep track of the progression here, to get from 1 to 2, I'm multiplying by 2. To get from 2 to 3, I'm multiplying, or 2 to 6, I'm multiplying by 3. Then I'm multiplying by 4. Then I'm multiplying by 5. So this isn't an arithmetic progression because I'm not adding the same thing. And it's not a geometric progression because I'm not multiplying by the same number. But this particular pattern of multiplying by 1, then by 2, then by 3, then by 4, then by 5, hopefully you've done enough of our Taylor series problems to recognize that those are exactly the factorial numbers. This is simply the factorial sequence. Keep in mind that 0 factorial, the very first term, is 1. So we have 0 factorial, 1 factorial, 2 factorial, 3 factorial. So not all sequences are arithmetic or geometric. Some of them are just, well, special collections of numbers. Moving on to our next sequence, the sequence Dn. Well, what patterns do you see in these things? 1/2, 3/5, 5/8, 7/11, 9/14, and 11/17. I'm certainly not adding the same thing to each term, and I'm not multiplying by the same thing each time, and I don't recognize factorials in here. This is an example of what's sometimes called a compound sequence, because there are individual parts that are behaving in terms of simpler pieces. For example, if I were to focus only on the numerators right now, the numerators go 1, 3, 5, 7, 9. They're going up by 2 each time. Since they're going up by 2 each time, that makes them an arithmetic sequence. And so the formula for any arithmetic sequence is the starting value, 1, plus the common adding times n. So each one of these numerators takes the form 1 over 2n. But what about the denominators? The denominators take the form 2, 5, 8, 11, 14. So I'm getting each one of these denominators by adding 3 each time. So I have a completely different arithmetic sequence for the denominators. Each one of the denominators is found by taking 2 and adding to it 3 n number of times. So I can handle the numerator by one arithmetic formula. I can handle the denominator by some other arithmetic formula. That means if I put a fraction bar through the middle of this, I've got a formula who gets the job done. And so we've managed to come up with a formula. The formula 1 plus 2n over, I need to erase myself some space here, 2 plus 3n. And so we've come up with a formula for the third sequence by essentially attacking each of the individual components, well, individually. So let's see if we can use the same trick on the next sequence. So in this next sequence, well, let's see, maybe we can try doing the numerator and the denominator trick the same way. If I take a look at what each of these fractions are, and I'm going to write this first one as 1 over 1, just so I can highlight a numerator and a denominator, the numerators go 1, 6, 11, 16, 21. Well, that pattern of 1 to 6 to 11 to 16 to 21 indicates that I'm adding 5 each time. So the numerator is an arithmetic progression, and the formula for an arithmetic progression is, well, you take the first value, 1, and then you add 5n. So cool, we have the numerators taken care of. Now, what about the denominators? So the denominators are 1, 5, 25, 125, 625. That pattern of 1, 5, 25, 125, 625, well, these are evidently powers of 5. I'm just multiplying by 5 each time. So it turns out that this denominator is a geometric progression. The formula for geometric progression is the starting value 1 times 5 raised to the nth power. So notice the comparison and the contrast between these two. Both of them involve starting with 1, and both of them are going up by 5 some way. But the numerators you're going up by adding, and in the denominators you're going up by multiplying. In either case, though, put that fraction bar through, and we've been able to recover the fraction. Well, almost. There is this one little aspect that I've sort of ignored here. There's this value in the front that's changing from plus, minus, plus, minus, plus, minus. How do you get plus, minus, plus, minus, plus, minus? Written like that, it's kind of, is that even a sequence? Is that a list of numbers? Well, maybe not written like that, but if you treat it as plus and minus 1 the whole way through, positive 1, negative 1, positive 1, negative 1, then you're looking at another geometric sequence. I get each new term in this value right here by multiplying by negative 1 each time. And so the term in front, that plus minus, is a geometric sequence. You're starting with 1, and then you're multiplying by negative 1 each time. So if we put all of the entries together, we've actually been able to cook up a formula for the nth term of the sequence En. So let me summarize what we've got there. The sequence En takes the form minus 1 to the n, that handles the plus minus in front. The numerator was the arithmetic sequence 1 plus 5n, and the denominator was the geometric sequence 1 times 5 to the n. And so we have a formula for our third sequence. This last sequence, f, is probably the hardest of the bunch. It's really easy to figure out what the pattern is. I'm adding an extra 3 to my decimal each time. But in fact, finding formulas for sequences is one of the most challenging problems that's actually out there. It can be terribly difficult to figure out an actual explicit formula for each one of these numbers. You could give it a try. In fact, pause the podcast right now and give yourself 10 minutes. See what you could do with this one. Turns out that coming up with a formula for this is a little bit tricky, and I'll at least walk you through the process. The basic idea of this is, well, let's first turn these into fractions. So this is 3/10. This is 33/100. This is 333 1,000ths. And then we have 3,333 10,000ths. The nice part about this is that the denominator in this is a geometric sequence. Each one of the denominators is going up by 10. That means whatever this sequence is, let's call it Fn, its denominator should be a geometric sequence starting at 10 and going up by 10 to the n, which I guess I could simply rewrite that as 10 to the n plus 1. Lost the brace. But how are you going to get those 3s, 3 to 3, 333, 3333s? How do you get those? Well, this one I'm going to have to be a little bit clever. I'm going to go and take each one of these fractions and multiply it by 3 over 3. So I haven't changed the fraction any. So on the bottom I have this extra 3. But on the top, well, let's take a look at what these numbers reduce to. 9. 3 times 33 was 99. 3 times 333 was 999, and this is 9999. So now you have a bunch of 9s up top. The cool thing about the number 9, though, is it's 1 less than this denominator. This 99 is 1 less than the red denominator. This 999 is 1 less than that. In other words, the numerators of each one of these sequences is the denominator take away 1. And so putting all of these pieces together, and we've come up with formulas for all 6 of our sequences. The second thing that I'd mentioned earlier was the idea of limits. So by way of example, let's see if we can find the limit of each of these sequences. Now, it might be sort of hard to motivate what that is in general, but it's actually really easy to motivate what it is with a specific case, the sequence f. The numbers 0.3, 0.33, 0.333, 0.3333. If I gave you that list, 0.3 and then a 33 and then a 333, and I looked really far down in that list at something like 0.3333, and say I'm looking at maybe the 10th or 12th term in here. So I have all of these 3's packed up. If I gave you that number, you would almost certainly not be thinking, oh, it's something like 10 to the 13th minus 1 over 3 times 10 to the 13th. You'd be looking at that and going, man, that thing is really close to a third. And the farther out in the sequence you go, the lower down in this list, the more 3's you add to it, the closer the approximation gets to 1/3. That's the general idea of the limit of a sequence. If an is a sequence, we say that the limit of the sequence an is the number L if the terms in the sequence eventually approximate L to any number of decimal places. So for example, that 0.33 sequence is approximating 3 to a new decimal place every single step of the way. So even though sequence is a new kind of function concept, we still are talking about the notion of a limit, about getting successively closer approximations of something. As a result, we're going to steal a lot of the limit language we've used before. For example, we say that the sequence converges to L, if this is true, or we say that L is the limit of the sequence. On the flip side, a sequence that doesn't converge to any number is going to be called divergent. So what does this mean geometrically? Well, imagine we stick up some axes, and then I start plotting the terms of a sequence. Bop, 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 bop. So I have the different terms of the sequence. What would it mean for this sequence to converge to L? Well, it would mean you'd have to have some magic value on that y-axis called L that had the property that as the sequence moved farther to the right, the terms would be getting closer and closer and closer to this value. So that every subsequent dot, farther and farther and farther to the right, is going to start to collapse more and more on this line. Now you might remember that that sounds an awful lot like the notion of a horizontal asymptote. And it would be. This is a horizontal asymptote for this graph that consists of nothing but dots. In the language of Calc 1, we would have written this as a limit as the input, as x tends to infinity, of some kind of a function. But since our functions are sequences, they don't have x's, they have n's. And so it would seem kind of reasonable that we might write this as the limit as n tends to infinity of an. And that's in fact an alternate notation. Instead of just saying the generic limit of a sequence, we can also say the limit as n goes to infinity of the terms an. We're just going to steal that notation. So imagine we were to go back to the 6 sequences we looked at the beginning, and I focused my attention on this last sequence right down here, the sequence of the 0.3s. I know in my heart of hearts that this limit is supposed to be a third, because these values are clearly numerically approximating 1/3. Could I somehow get that information out from the formula as well? Well, let's sort of think about this for just a second. We've got the sequence 10 to the n plus 1 minus 1 over 3 times 10 to the n plus 1. And we want to take the limit of this sequence. Now remember that the other notation for the limit of a sequence is we can say it's the limit as n goes to infinity of this formula right here. But that looks a heck of a lot like what we were doing in Module 2. That looks like something that L'Hopital's rule would just sort of take over. Right? If we were to plug in n going to infinity, that would be 10 to the infinity plus 1 minus 1 over 3 times 10 to the infinity. Now since these, plus 1, sorry. Since these aren't indeterminate forms, I'm allowed to use my intuition. My intuition here, if I took a big number, raise 10 to a big number and subtract 1, that's going to be a huge number. And on the flip side, if I took 10 to a big number and multiplied it by 3, that's also going to be a huge number. So I'm looking at an infinity over an infinity, which means I could apply L'Hopital's rule to this thing. So I'm going to hit it with the L'Hopital stick. Well, the first thing I got to do to apply derivatives is I'd have to prep this. So this is e to the power of n plus 1 times ln of 10 minus 1. And on the bottom we have 3 times, again, let's prep it, this is e to the power of n plus 1 times ln of 10. And now I can hit it with the L'Hopital stick. So if we differentiate the top, let's see, the derivative of e to the blank is e to the blank times the derivative of the blank. The blank is n plus 1 times ln of 10. The derivative of that, well, remember, ln of 10 is a constant, so it's just going to come along for the ride. The derivative of n plus 1 is 1. So cool, we've taken care of this derivative. The derivative of 1 is 0. And so I can now focus on the bottom. The derivative of the bottom piece, well, the 3 comes along for the ride. And the derivative of e to the n plus 1 ln of 10 we've just worked out. That's e to the power of n plus 1 times ln of 10 times ln of 10 times 1. So now let's clean this up just a wee bit here. On the top, let's see, we've got ln of 10 times 10 to the n plus 1, just by deprepping it. And on the bottom, let's see, we have a 3 times ln of 10 times 10 to the n plus 1 by deprepping that. You notice that the ln of 10's cancel. Oh, the 10 to the n plus 1's cancel. And so this means we're just looking at the limit as n goes to infinity of 1 over 3. And since that's a pure constant, we get a 1/3. And so check it out. Our sequence of 0.33333s converges to 1/3, which is what we have been told since, what, 3rd grade, and now I can believe it. There's only one problem with this calculation, and that's that every single step in it is completely and utterly flat out wrong. How could every step of this be flat out wrong? Well, here's the problem. Let's graph this real fast. If I were to graph what this is, the first term was 3/10. So maybe that's right around here. The next term was 0.33, so it was a little taller. The next term was 0.3333, so it was a little taller. The next term was 0.33333, so it was a little taller here. I know that these things are supposed to be honing in on the value 1/3, so I'm clearly not drawing this thing to scale. But the scale is not the thing I want to focus on. Look at the work that we did. We used L'Hopital's rule right here. L'Hopital's rule means you're looking at functions who are differentiable. But look at our sequence. Our sequence is not a differentiable function. Think about it. Each term of our sequence is an isolated single dot right here. If I asked you, quick, what's the tangent line to that dot right there? That sentence doesn't make any sense. There are these huge breaks in between each one of these points. These are about as not differentiable, as discontinuous as you could expect. And because this is so discontinuous, none of the tools that we've developed in the whole of Calc 1 or Calc 2 apply to a sequence in general. Sequences are a new and different beast. In fact, the entire study of sequences is what's called advanced calculus. And in advanced calculus, also called real analysis, you learn the techniques for dealing with limits of sequences. It turns out that that's a much, much harder subject. There are a number of techniques for computing the limits of sequences that have exciting names like the Cauchy criterion, if I get that right. There's also something called the monotone convergence theorem. There are things known as comparison tests. And in fact, an entire whole theory of calculus is dedicated to working out a problem like this, the limit of a sequence. Now, limits of sequences are going to be important to us, but we don't have the time to develop an entirely new suite of calculus rules for it. So what we're going to do is we're going to piggyback off of Calc 2. We just have to be careful about it. So let me motivate what we're going to do, and then we'll come back and fix up this example. So let's suppose that we have some sequence. And so I'm just going to make a sketch of my sequence. It's got dots evenly spaced apart. But there's sort of no rhyme or reason in between these things. But let's just not say it's some random sequence. Let's suppose that we have a function who has two properties. So let's suppose that f of x satisfies the following two properties. Property number one, f of n is equal to a of n for the values n equals 0, 1, 2, 3. So in other words, f is some kind of a function, and it's a function who, whatever its curve looks like, manages to pass through each one of these dots. So think of it as the sequence is a bunch of dots, and the function connects the dots. But I'm also going to add a second criterion, that the function f of x has only a finite number of critical points. So remember, critical points are discontinuities and bends on a function. So by saying it has a finite number of critical points, what I'm trying to prevent is me from doing something like this to connect the lines, by making the function wobble around, putting in horizontal or putting in vertical asymptotes, making it just sort of crazy and oscillatory. So together, the first line says I want to connect the dots, and the second line says I want to sort of smoothly connect them without adding a whole bunch of extra bends to it. So if I could find and get a hold of something like that, well, then what's going to happen? Well, such a function only has a finite number of critical points. There's a bend, there's a bend, there's a bend, there's a bend. So that means that eventually it's got to stop being oscillating. Since every single one of the dots in the sequence is forced to live on this by the first property, what it means is that if the function flattens out and has a horizontal asymptote at some magic value L, then every single one of the dots on the sequence, because they live on the graph of the function, is going to have a horizontal asymptote at L2. In other words, if you have a function that satisfies these things, then the limit of the sequence an is the same thing as the limit as x tends to infinity of the function f of x. We call such f's that have these properties underlying functions. So this is an underlying function for the sequence. And this result right here is sometimes called the underlying function principle, or the underlying function test. So if you can do this, then you could change a sequence limit for a module 2 limit, and the job would work just fine. So let's go back to our previous example. We have the limit of the sequence 10 to the n plus 1 minus 1 over 3 times 10 to the n. Now we could ask ourselves, the terms of the sequence are 10 to the n plus 1 minus 1 over 3 times 10 to the n plus 1. What would happen if we changed all of these n's into x's? 10 to the x plus 1 minus 1 over 3 times 10 to the x plus 1, and treated this as if it was a function. Well, let's take a look at what this function is. Does this make sense as a function? Could you plug in more numbers into here? Well, yeah, we've in fact prepped it before. This is really nothing more than a special exponential. It's e to the x plus 1 times ln of 10 minus 1 over 3 times e to the x plus 1 times ln of 10. Right, so this is a completely ordinary function. If I plugged in whole numbers, then my formula f of x is going to match this guy. But this is just built out of exponentials, right? It's a ratio of two different exponentials. Exponentials don't have any critical points whatsoever. And so our expectation is that this should only have a finite number of critical points. And so that means this is an underlying function. So the underlying function principle says, instead of working out the limit of this sequence, we can exchange it for the limit as x goes to infinity of this function right here, 10 to the x plus 1 minus 1 over 3 times 10 to the x plus 1. Now if we continue with the work that we had done before, then we would have come up with the same 1/3. Formally, it looks like we're doing the same work, but there's a big and important step here. And the important step is saying that the sequence that we're looking at is nice enough that it could be expressed in terms of a Calc 1 function. That's going to happen quite a bit, but it's not a guarantee. So let's go back and take a look at our other sequences. So we've just shown that our last sequence converged to 1/3. What about the other sequences? Well, let's take a look at this first sequence. What would be the limit of the sequence 1 plus 3n? So we could say, all right, each one of these terms is equal to 1 plus 3 to the n. If I replaced all of those n's with x's, it's a cosmetic change, but I'm changing how I'm thinking about it. I'm not thinking of this as dots anymore. I'm now asking a question about a specific line, the function 1 plus 3x. Well, that's just a straight line, right? That's a line of slope 3, y-intercept 1. It clearly doesn't have any critical points whatsoever, and so it's an underlying function. So the underlying function principle says that to work out the limit of the sequence, it's the same thing as to work out the limit as x goes to infinity of 1 plus 3x. The function 1 plus 3x. And now we're allowed to use any of the tools we've developed in Calc 1 and Calc 2. If I just directly plug in, I'd get 1 plus 3 times infinity. That's not an improper form, or indeterminate form, so I can use my intuition, and my intuition says that 1 plus 3 times a big number is frickin' huge. And so that tells me that this limit right here diverges. And so since the function diverges, the underlying function principle tells me that the sequence does the same thing. So my first sequence diverges. I guess sort of in hindsight too, that makes sense. I mean, look at these numbers. It's clear that these numbers aren't being decimal approximations of anything. They're getting bigger and bigger and bigger. The same thing would work for the sequence 2, 3, 18, 54, 162. They're getting bigger and bigger and bigger. And also true for the n factorial sequence. Right, I don't really need my highfalutin tools for that. But these last three are worth spending some time on. So let's take a look at the sequence D. What is the limit of 1 plus 2n over 2 plus 3n? So we want to work out the limit of this sequence, or in alternate notations, the limit as n goes to infinity of 1 plus 2n over 2 plus 3n. The underlying function principle says that that's the same thing as the limit as x goes to infinity of 1 plus 2x over 2 plus 3x, where I'm now thinking of this as an actual honest-to-goodness function. But you sort of have to ask yourself, all right, how many critical points can this thing have? Remember that the critical points are all about discontinuities and bends, local extrema. Well, just by looking at it, I can tell it only has one discontinuity. Working out the exact number of bends, well, I could take a derivative and find critical points, but it's worth pointing out that there's nothing in here that has trig in it. And so trig is the only set of functions we've ever seen that have an infinite number of bends. So I know that this is going to be finite. So put it together, this only has a finite number of critical points. And since we've checked that, the underlying function principle is now valid. So I can go and take the derivative of, I can take this limit using any of the tools we've got. One minute for computing this limit, I could go and plug things in. If I plug in, I'm going to have an infinity on the top and an infinity on the bottom, which means that I could apply L'Hopital's rule. So let's hit this with the L'Hopital stick. I take the derivative of the top and the derivative of the bottom. The derivative of the top will be 2. The derivative of the bottom will be 3. And then if I take the limit of that as x tends to infinity, well, that's just the constant 2/3. And since I got a number, that's my value. So the limit of this sequence is 2/3. Let's try to take the limit of the sequence 1 plus 1 over n to the nth power. Again, remember the alternate notation is this is the limit as n goes to infinity of the terms 1 plus 1 over n to the nth power. So according to the leading term test, I can swap this out with a new limit. The limit as x tends to infinity of 1 plus 1 over x raised to the x power. And all I have to do is make sure that this function right here only has a finite number of critical points. And that means I'm really just going to make two quick checks on the side here. I'm going to take a look for discontinuities. Where is this function discontinuous? Well, the only denominator who pops up in it is right there at x. So it's discontinuous at x equals 0. It's got one discontinuity. The other thing I want to do is I want to check for how many bends does a function like this have. I could work that out explicitly by taking a derivative and solving for it. But remember, the thing I only care about is whether or not there's an infinite number. And since there's no trig anywhere in here, right, if I prep it too, just to make sure that we all agree, prepping it, this is going to be e to the power of x times ln of the base, 1 plus x to the negative 1. And in its prepped version, I can see logarithms and I can see exponentials, but no trig. So put it together, whatever there is bends, there's less than an infinite number of them. So since it has a finite number of bends, I know that this is, in fact, an underlying function, and I can use the underlying function test. Forgetting I have this bottom bit for the time being, let's go back up to the original limit and start with my evaluation trick. Well, the first thing I do is I plug in an infinity. That gets me 1 plus 1 over infinity to the infinite power. We know that 1 over infinity can be interpreted as a 0 in a limit, and so this is really 1 to the infinity, which makes it a type C indeterminate form. So since it's a type C indeterminate form, I need to rewrite it as an exponential and move the limit up. Check that out. Apparently writing it as an exponential does pay off. So I can write it this way, move that limit up to the top, so this is e to the limit as x tends to infinity of x times ln of 1 plus x to the negative 1. And then this limit up here, I can focus on separately. So if we take a look at that limit, this is the limit as x tends to infinity of x times ln of 1 plus x to the negative 1. If we plug in infinity, that's going to get me an infinity times ln of 1 plus infinity to the negative 1. Now, infinity to the negative 1 is not indeterminate. That means I can use my intuition. The reciprocal of a really big number is a really small number. So we're actually looking at an infinity times ln of 1, and ln of 1 is the number 0. So this is an infinity times 0, which makes it a type B indeterminate form. To deal with type B indeterminate forms, we need to rewrite this as a giant fraction. Maybe the easiest way to write it as a fraction is take this x right here and move it underneath the fraction bar as an x to the negative 1. And I'll leave the ln of 1 plus x to the negative 1 by itself. I can now try to reevaluate the limit. If I plug in my infinities, I get ln of 1 plus infinity to the negative 1 over infinity to the negative 1. Well, we just saw just a second ago that this evaluated to 0. On the other hand, infinity to the negative 1 we also saw evaluates to 0. And so this is something that L'Hopital's rule applies. Type A indeterminate form. So if we apply L'Hopital's rule, we hit it with the L'Hopital stick. The derivative on the top, well, the derivative ln of blank is 1 over blank times the derivative of blank. The blank is 1 plus x to the negative 1. The derivative of that is negative x to the negative 2. The derivative on the bottom, on the other hand, is going to be negative x to the negative 2. And actually, that negative x to the negative 2 in both places cancels, and so this simplifies to being the limit as x tends to infinity of 1 over 1 plus x to the negative 1. If we plug in our infinities, that's 1 over 1 plus infinity to the negative 1. We just said that infinity to the negative 1 is a 0. And so this evaluates to 1 over 1 plus 0, which is 1. So we've just worked out that the limit is 1. Now remember, that was just the limit up in the exponent. So our final tally is this is equal to e to the power of 1, which is just the number e. And so the limit of the sequence 1 plus 1 over n to the nth power is equal to e. So we're almost done evaluating all 6 of our original sequences. The only one we haven't done here is sequence e. Minus 1 to the n, 1 plus 5n over 5 to the n. So let's see what we can do with this one. What is the limit of negative 1 to the n? 1 plus 5n over 5 to the n. So this is the same thing as the limit as n goes to infinity of negative 1 to the nth power times 1 plus 5 to the n over 5 to the n. So in keeping with what we've been doing before, we could attempt to apply the underlying function principle. And essentially the basic idea of the underlying function principle is we changed all of those n's to x's, and then we asked whether or not this function right here has a finite number of critical points. If it does, we're good to go. So let's sort of make a quick count of where is this function discontinuous. Well, the denominator is an exponential. That's never discontinuous. The numerator is honky-dory. It's a line. But what about this thing? Where is negative 1 to the x discontinuous? You might be tempted to say, oh, it's an exponential. Nothing bad happens to it. But that negative 1 is a problem. For example, what's negative 1 to the 1/2 power? Well, if you plug in negative 1 to the 1/2 power, that's the square root of negative 1. But the square root of negative 1 is an imaginary number, which means this value is not in the domain of the function. It's discontinuous at 1/2. In fact, the same thing would be true for negative 1 raised to any fraction with an even power, even denominator, because that's going to be asking you to take an even root of negative 1. And even roots of negative numbers are not real. So it turns out that this thing right here is discontinuous at every fraction with an odd number, every fraction with an even denominator. It's actually worse than that. Because if you tried to plug in pi, negative 1 to the pi power, what does that even mean? The best you might try is you might try to convert this over using our conversion formula as e to the power of pi times ln of the base. But then that, ln of negative 1, remember the graph of our logarithm? It died at 0. You can't even get over here to negative 1. I have no idea even how to make sense of negative 1 to the pi. So it turns out that this minus 1 to the negative x is discontinuous infinitely often. So that means that this formula here is not an underlying function. We cannot go and use the toolkit we've got. So this idea has been thrown out for us. Not every sequence has an obvious underlying function. So it turns out that this particular approach isn't going to work for me. That function minus 1 to the x is just a bad function from a calculus point of view. So what could we do with it? Well, do you remember what that minus 1 to the n does? If we just focused on minus 1 to the n, it was the sequence plus 1, minus 1, plus 1, minus 1, plus 1. It was the sequence who caused sign changes. So what if we focused only on the even terms for just a second? What do the even terms A0, A2, A4, A6 look like? Well, the formula for these terms A sub n, where n is an even number, well, let's see, the formula for any of the A sub n's is minus 1 to the nth power times 1 plus 5n over 5 to the nth power. But if n is an even number, then minus 1 to an eventh power, this thing is always just going to be 1. And so effectively, for the even terms, the sequence just looks like 1 plus 5n over 5 to the n. So if I wanted to take the limit as n goes to infinity of just the even terms, that's the same thing as taking the limit as n goes to infinity of just the sequence 1 plus 5n over 5 to the nth power. Now this time, if I were to go and swap all of those n's with x's, the limit as x goes to infinity of 1 plus 5x over 5 to the x, then this beast right here is definitely an underlying function. Because the top is a line, the bottom is an exponential. The exponential has no discontinuities, so this function is continuous everywhere. And because it has no trig in it, it can only have a finite number of critical points. So I could go and use any of the tools in my calc arsenal. I'll plug in infinity. I'm going to have an infinity on the top and an infinity on the bottom. That means that this is L'Hopitalable. The derivative of the top, if we apply L'Hopital's rule, is just going to be 5. The derivative on the bottom, well, this is an exponential in hidden form. If I prepped it, that would be e to the power of x times ln of 5. And so the derivative of that will be the exponential times the derivative of the exponential, which is ln of 5 times the exponential 5 to the x. If I now let x tend off to infinity again, we're going to have 5 on the top, and on the bottom we're going to have an infinity. 5 over infinity is not indeterminate. It, in fact, evaluates to 0. And so we've just shown that the even terms converge to 0. In symbols, we might write it this, that the limit of the even sequence, the sequence of even terms, is equal to 0. So what does that say about the actual limit? Well, it doesn't say anything, because remember, for a sequence to have a limit, every term has to become a better and better decimal approximation of the limiting value. What we've just shown is that every one of the even terms is becoming a better and better approximation of 0. Well, what if we did the same thing, but we looked at all of the odd terms? If we compared the even terms and the odd terms, well, we've compared every single term right here. If we could show that every single one of the odd terms also converged to 0, that means every single even term is a decent approximation of 0, every single odd term is an approximation of 0, and those two things together would tell me that this limit would be 0. So how do we handle the odd terms? Well, we can attack it the same way we did before. Let's take a look at a sub n on the assumption that the n is an odd value. Now the formula for every single a sub n is negative 1 to the nth power times 1 plus 5n over 5 to the nth power. But if n is odd, then minus 1 to the odd power, minus 1 to the first, minus 1 cubed, minus 1 to the fifth, is simply going to evaluate to being minus 1. In other words, if I want to go and take the limit of the sequence an, where these are all the odd values, that's the same thing as taking the limit as n goes to infinity of negative 1 times 1 plus 5 to the n over, 1 plus 5n over 5 to the n. If we swap this out for an underlying function, the limit as x goes to infinity, we're going to have negative 1 plus 5x over 5 to the x. Well, take a look at this. This is exactly the function we had last time. And we've already said that this function is an underlying function. It has no discontinuities. It can only have a finite number of bends, so it has a finite number of critical points. And in fact, our work last time showed that the limit of this function was equal to 0. And then, of course, there's a minus who comes along for the ride. But the limit of negative 0 is still 0. And so, yep, the even terms converge to 0. The odd terms converge to 0. And so we've just shown that the limit of negative 1 to the n, 1 plus 5n, 5 times n, over 5 to the n, is in fact equal to 0. And so we've been able to do a complete analysis on the 6 sequences. Let's try this idea one more time. Let's let an be the sequence 3/7, 5/17, 7/27, 9/37, 11/47, ... and bn be the exact same sequence except alternating in sign. And let's compute the limit of the sequence an and the limit of the sequence bn. Now for the sequence an, this first problem, well, in order for me to work out the limit of the sequence an, it's going to be helpful if I had a formula for each one of those individual terms, because a formula will dictate whether or not I can do the underlying function principle. So let's see if we can come up with a formula for this thing on the fly. Now, a lot of times we try to focus on numerators and denominators separately, so let's see if that trick will work here. In my numerators, they go 3, 5, 7, 9, 11. Pretty quick assessment, they're going up by 2's each time. So the top is an arithmetic progression, and arithmetic progressions have the same formula. The first term plus the constant increase 2 times n. Well, can we pull the same stunt off for the denominator? The 7, 17, 27, 37. Well, evidently they're going up by tens each time. So the bottom is a separate arithmetic sequence, starting at 7 and going up by tens each time. And so we've got the sequence 3 plus 2n over 7 plus 10n. Now that I'm armed with the sequence, I'm going to change all of those n's to x's and see what I get by treating it as if it was a function. So now I have the x's in here. Remember, this is more than a cosmetic change. You're now sort of thinking this is an honest-to-God function, not just something that you plug numbers in, integers into. So if I take a look at this thing, it's got one discontinuity, right? It's discontinuous at x equals negative 7/10. Because the top is a line and the bottom is a line, it can only have a finite number of bends. It's a rational function. They don't get that many bends here. And so put it together, finite number of bends, a single discontinuity. This has a finite number of critical points, and that means it's an underlying function. And since it's an underlying function, we are allowed to use the underlying function test. Now I just got to go and compute this limit using any techniques we'd like. I'm actually going to try and, vary things up a little bit. I'll use the leading term test this time around. So this is the limit as x tends to infinity of 2x over 10x. Well, the x's cancel. 2 goes into 10 5 times. And so that's going to get me the limit as x tends to infinity of 1 over 5. And since the limiting value of that is just the constant 1/5, that means that's the limit of our sequence. So we've just shown that the sequence an converges to 1 over 5. How about the sequence bn? Well, let's see if we can find a formula for the sequence bn. If we try the same trick that we had last time, to work out the limit of a sequence, we want to come up with a formula for each one of those individual terms. So this is going to be the limit as n goes to infinity. And our point was, the idea of the sequence is it has all of the same numbers as the sequence an. So the fractions will still be the same thing. 3 plus 2n over 7 plus 10n. The only thing that's different now is that you have this additional sign changer. But the easiest way to get something who just goes plus minus is to take -1 and raise it to the nth power. It's just a geometric sequence, starting at 1 and going up by -1 each time. And so now we've got a formula for the second piece. So now that I have a sequence, we can see if we can apply the underlying function principle. I'll replace all of those n's by x's, so I have -1 to the x, 3 plus 2 times x over 7 plus 10x, and then I'll go through the same arguments before. Where is it discontinuous or not? Well, hopefully you'll remember that this thing right here, -1 to the x, is discontinuous infinitely often. It's discontinuous at most fractions and at every irrational number. That means it has an infinite number of critical points. And so the underlying function test is dead for this. This is not an underlying function. So we've got to go and try something else. Well, we could try to do the even and the odd trick. If we looked at the even terms, the limit of the sequence bn, where we only focus on the even terms, that's going to be the limit as n goes to infinity of, well, let's see, every single term looks like -1 to the n, 3 plus 2n over 7 plus 10n. But when n is even, this term simply vanishes. And so now what I'm looking at is I'm looking at the limit as n goes to infinity of 3 plus 2n over 7 plus 10n. And that's actually the exact same thing as our original sequence an. So the work we did before shows that this converges to 1/5. The even terms converge to 1/5. What about the odd terms? If I took a look at the limit of the sequence bn, but I focused only on the odd terms, that would be the limit as n goes to infinity. Again, every single term looks like -1 to the n, 3 plus 2n over 7 plus 10n. But now, on the assumption that each one of these terms is odd, then minus 1 to the n is actually just always minus 1. And so I'm going to have the limit as n goes to infinity of negative 1 times 3 plus 2n over 7 plus 10n. And the exact same argument before, if we use the same underlying function that we had before, we know that that piece is going to converge to 1/5, but we're going to have this extra negative 1 floating out in front. And so it turns out that the odd terms converge to negative 1/5. Let's say that again. We have this sequence right here. If we work out the terms, then it turns out that every single even term is a decent approximation of 1/5. So pretty much all of the even terms are going to look like 0.2 and change. But every single odd term is a decimal approximation of negative 1/5. Remember that the definition of a limit said that you had to be approximating a single value, and this isn't. It's trying to oscillate between two other ones. And so our only conclusion is that this sequence cannot converge. So we're going to write that the sequence Bn diverges. And we sometimes say it diverges by oscillation, because every other term is jumping back and forth between two different values.